are essentially descriptors of the accuracy of a test. And the way we can think about sensitivity is as follows, that the greater the sensitivity, the more likely that specific screening test will detect persons who have the disease. And a negative result on a test with excellent sensitivity can virtually rule out all disease. Similarly, the specificity is interpreted as if the greater it is, the more likely it is that persons without the disease will be excluded. And similarly, a positive result on a test that has an excellent specificity will strongly suggest the presence of a disease. So let's go through an example. This is an example of screening for diabetes using glucose tolerance testing. And in this particular sample, we have 150 persons who truly have diabetes, but again, this is a screening test, so they're not presenting clinically with signs and symptoms of diabetes. And then we have 9,850 who do not. So among those who have diabetes, in our glucose tolerance test, 34 of those were positive. The test yielded a positive result based on some criterion that was pre-specified to serve as the value. If the person's value is above that, then they are considered to have diabetes, and if they're below it, they're considered to not have diabetes. So therefore, the calculated sensitivity of this example would be 22.6%, which, by the way, is rather low. In contrast, I should say, the specificity comprises all those who do not have disease but who test negative, which in this case was 9,830 persons, divided by the 9,850, and we get a very high specificity of 99.7%. So in this example, we can conclude that this particular approach to screening for diabetes is highly specific in that it has a great ability to correctly identify persons who do not have diabetes. However, it's poorly sensitive, so it's not strong in correctly identifying persons who have the disease. So now I want to shift and talk about two other measures that are used when understanding or interpreting results from a screening test. And these are called predictive values. And these are essentially estimates of the probability of the presence or absence of the disease based on the test result. So in a sense, it's the reverse logic or thinking to that we just discussed in terms of sensitivity and specificity of a test. So specifically, the positive predictive value of a test is the percentage of persons with a positive test who actually have the disease. And it provides us a measure of how likely it is that the disease of interest is present, given that the test is positive. And then the other option is the negative predictive value, which is essentially the reverse scenario, which is the percentage of persons with a negative test who do not have the disease of interest. And it provides us with the answer to how likely is it that the disease of interest is not present if the test is negative. Now, I will say that the predictive values are measures that are considered useful or relevant at the individual level from a clinical perspective. So it is the negative and positive predictive value that a healthcare provider is most interested in when they're choosing when or not to use a screening test. It is, from a public health perspective, sensitivity and specificity are the measures that are of most use. Okay, and we'll discuss that more in a bit. So in terms of calculating the predictive values, we now are interested in the rows of our 2x2 table. The 2x2 table is set up the same way as it was before, with the disease down the columns and the outcome of the test along the rows. However, now we're going to be interested in the row sums, if you will. So the positive predictive value itself is the number of true positives who have the disease, which is the A value, divided by the sum of all test positive individuals, so A plus B. And so again, it gives us a value of it gives us a proportion or a percentage of the true positives, A, divided by all who tested positive, or A plus B. And then the negative predictive value would be the true negatives, or the D cell, divided by the sum of the the sum of the C and D cells, consisting of the test negative values. So D over C plus D, to be interpreted as the true negatives over all who tested negative. So going back to So now to go through an example of calculating the positive and negative predictive values, we're going to discuss an example where we have a test for glaucoma, and that specific test is to evaluate the pressure intraocularly. So the pressure on the eye, and a value of a certain amount is viewed as a person having glaucoma, and anything below that value, a pressure value below that, would essentially say that a person does not have glaucoma. And we'll talk about in a bit how those values are chosen, right? So nonetheless, in this example, we have 140 individuals who test positive for glaucoma, and I also have glaucoma, over 220 individuals who tested positive. So that provides us with a positive predictive value of 140 over 220, as I said, which is a value of 64%. The way that can be interpreted as saying, among those persons who test positive, the proportion who truly have glaucoma is 64%. The negative predictive value would be the number of people who test negative and who don't have glaucoma, which is 910, divided by the sum of all who test positive, which is 910 plus 10, or 920. And here we get a proportion of 99%, which is a very high negative predictive value. And it's essentially telling me, as a clinical person, that among those persons who come in and who test negative for glaucoma, 99% of the time they will not have glaucoma. Okay? So in this scenario, we have a high negative predictive value and a low, well, it's a marginal positive predictive value. So it will provide reassurance to the clinician that should the test be negative, the person does not have disease. However, it's not as useful for us in terms of the people who tested positive and the probability that they have the disease.